Dear colleagues, my name is David Bondartsev, and on behalf of the co-authors, I will present the paper with the title Heat Transfer for the Boiling Crisis in Porous Systems. Modern technologies play an important role in the production of mechanical engineering products. Among the most promising ones are nanotechnologies and plasma processing methods that allow to create porous coatings on the surfaces of products, which simultaneously serve as reservoir and a vehicle for lubricants, ensuring long and efficient operation of rubbing parts and units. One of the promising and effective methods of intensification of heat exchange is the use of highly conductive capillary porous and mesh materials. Such materials have long been used in liquid propellant rocket engines as filters, as capillary intake devices in the manufacture of permeable firing bottoms of mixing heads and other devices. An important feature is the possibility of making porous materials, the workability and area of application of which are determined by the pore structure. Porous materials are strong and resistant to corrosion, can operate in a wide temperature range depending on the type of material. They do not clog the filtered liquid with filter products, are easily machined and welded, allow multiple regeneration, have high thermal and electrical conductivity. Development of various heat exchange intensifiers for cooling of combustion chambers and nozzles was performed on a rocket-type flame jet burner with a porous cooling system as shown on Figure 1. With 1 is marked the jet burner, combustion chamber, and supersonic nozzle. Nozzles are cooled by capillary porous system marked with 2 and 3 is casing. Combustion chambers and supersonic nozzles were investigated up to their destruction. Further development of the cooling system of combustion chambers and supersonic nozzles, especially for the highly forced modes of their operation, was the fact that the main drawback of the burner is the low service life due to the low reliability of the cooling system, especially in the high temperature zone, surge zone, on the critical section and the diffuser part of the level nozzle as a result of the following reasons. Figure 2 shows the burner and the combustion chamber is denoted with 1, a level nozzle with 2, with confuser 3 and diffuser 4 parts and critical section 5 between them, swirl 6, atomizer 7, and distribution head 11, which with branch pipes 12, 13, 14 for supply of oxidizer 19 and fuel 20 to combustion chamber 1 and coolant 18 to the cooling cavity 10 formed between shell 8 and the outer walls of combustion chamber 1 and level nozzle 2, installed in the housing 8. The casing 8 has holes 9, 21 for outlet of the coolant 18. The diffuser part 4 of the level nozzle 2 is provided with an insert 15 having a capillary porous coating 16 on the side facing the cooling cavity 10. Capillary porous coating 16 is made of multi-layer grid. The size of cells in each of them layer increases in the direction of the outer surface of the coating and is 0.08, 0.14 and 1 millimeter. The radius of cultivate of growth 17 is 2.5 to 5 times greater than its depth. Combustion products 22 are drained from the diffuser part 4 of nozzle 2. The coolant 18 is supplied to the branch pipe 14, leaving the coolant moves in the cooling cavity 10, formed between the shell 8 and the outer walls of the combustion chamber 1 and the level nozzle 2, consisting of the confuser 3 and diffuser 4 parts separated by the critical section 5. The gas stream formed of the combustion chamber 1 with a temperature over 2000 to 2500 degrees Celsius is accelerated to the necessary velocities 1600 and 2000 meters per second. in the level nozzle 2 and is thrown on the object of treatment of cutting in the form of combustion product 22. The burner operates in the detonation combustion mode, with the combustion product 22 pulsating due to the shortened diffuser part 4 of the naval nozzle 2. The presence of capillary porous coating 16 ensures creation of uniform and stable pulsating film of coolant 18 on the insert 15 from the outer and front sides under the joint action of internal forces and capillary forces. By making the capillary porous 16 anisotropic, that is, having successive growth of cell size in the direction of the outer surface, a high capillary pressure is created and possible vapor bubbles are actively. Thus, the burner has a long service life due to the intensification of heat transfer, entrainment of dissipated thermal loads, leveling of the temperature fields in the cooled walls, increasing the heat storage capacity of the nozzle, and the capillary porous opening ability to level thermal loads, which is especially important at the time of possible energy situations. The service life of the burner is increased 1.5 times due to the intensification of heat transfer by creating a uniform stable pulsating film on the outer surface of the nozzle, as well as by increasing the dissipated heat load through the high heat storage capacity of the insert with a groove made in it and capillary porous coating having anisotropic structure. Thus, the temperature field in the heat-stressed elements of the burner is leveled and the appearance of sharply varying destructive loads is excluded. The listed advantages are realized both at nominal load and at alternating and emergency operation modes. No blockage of the cooling cavity by steam bubbles. Coolant consumption is drastically reduced by a factor of 4, which saves water. The main heater was made of nichrome foil and thickness from 0.05 to 0.7 times 10 to the power of negative 3 meters, or stainless steel plate that is 1 and 2 times 10 to the negative of 3 meter. The length of the heated was 0.05 to 0.03 meters. The height was from 0.15 to 0.7 meters. The electric current was fed through copper electrodes with a diameter of 30 times 10 to the negative of 3 to the power of negative 3 meters. 0.0 times 10 to the negative of 3 meter thick accrete acted as electrical insulation between the wall and the nichrome. Radiant heating and surface heating by direct passage of alternating electrical current through the wall and the adjacent porous structure was also used. The structures were made of smooth woven brass, copper, and stainless steel meshes of simple and twill leaf and consisted of 1, 2, and 3 layers. When studying the beginning of liquid boiling, the power of net layer was up to 9. The cooling surface was made of stainless steel, brass, copper, bronze, nickel, aluminum, and glass. The wall thickness was 0.5 to 1 and 2 times 10 to the power of negative 3. The balance discrepancy between the heat supplied by steam in the condenser and the heat removed by circulation water did not exceed 11%. The material balance discrepancy between the coolant flow rate, discharge flow rate, and condensate flow rate did not exceed 10%. Experiments were performed with water for pressure from 0.01 to 10 megapascals, as well as with an equation solution of the following agent type PO1. The velocity of the fluid took values 1.1 times 10 to the power of negative 3 and 0.1 meters per second. Under heating, from 0 to 20 kelvins. The excess fluid was 1 to 14 from the steam consumption. The heat load was 1 to 60 times 10 to the power of negative 4 watts cubic meter. Thermal pressure was 1 to 60 kelvins. System orientation relative to the verticals from 0 to 90 degrees. From the analysis of experimental data revealed, for the heat flows, Q equals 1 to 8 times 10 to the power of negative 4 watts cubic meter. Boiling mode was transitional. For this mode, a significant effect of coolant flow rate and type of structure was found. This is especially pronounced for grids with large mesh size. These characteristics are close to thin film evaporators. Later boiling of liquid in comparison with the heat pipes is caused by distribution of heat fluxes of discharge and boiling. Some degrees of heat transfer coefficient with increase of Q value is connected with vapor bubble arising, reaching certain sizes and increasing thermal resistance of boundary layer. For the area of development, bubble boiling, Q greater than 8 times 10 to the power of negative 4 watts cubic meter, up to the critical thermal loads without destruction, no noticeable influence of the liquid flow rate within its variation, 1 to 7.5 was found. No information in the heat transfer capacity of the system for different cell size of the structure as in press pipes is noticed, because neither increased hydraulic resistance of the structure nor a decrease in capillary absorption limits the flow of fluid. It is not reasonable to significantly increase the coolant flow rate because there is a redistribution of flush and boiling flows, which makes the system more expensive. Therefore, it is advisable to introduce the concept of optimum liquid excess, which establishes a uniform temperature viewed along the height and length of the heat exchange surface. The optimal fluid flow rate is determined as follows. Up to the value of Q less than or equal to 10 kilowatt cubic meter, the flow rate is maintained close to the mode of operation of heat pipes at the hydraulic diameter 0.28 times 10 to the power of negative 2 meters and 30% for values greater than 0.28 times 10 to the power of negative 3 meters at Q greater than 10 kilowatt cubic meters, exceeding the flow rate by 1.3 to 2 times for the value less than or equal to 0.28 times 10 to the power of negative 3 meters. Allows to expand the range of removal of the value of Q in 2 to 3 times in comparison with heat pipes. At large angles of inclination, the dependencies are pronounced, especially for structures with low capillary potential. This confirms that the forces of gravity, the main transport, and capillary are used for uniform distribution of fluid in the pores and capillaries of the structure, and the greater the capillary potential of the structure, the more uniform distribution of temperature in the wall at different values Q. Comparison with heat pipes for Q greater than 10 kilowatt cubic meters shows that the intensity in the heat pipes is lower than 40%, or they are not operational. At Q less than 20 kilowatt cubic meters, heat pipes have a high density. In area from 2 to 10 times 10 to the power of negative 4 watt cubic meter, satisfactory agreement of experimental data is observed. For various technical devices and systems, a new porous cooling system has been proposed and studied, in which the coolant is supplied under the combined action of capillary and gravitational forces. The cooling surface was made of stainless steel, brass, copper, bronze, nickel, aluminum, and glass. The wall thickness was 0.5 to 2 times 10 to the power of negative 3. Visual observations were performed using holographic interferometry and high-speed filming using a film camera SKS-IM. The experiments were performed with water at pressure 0.0 and 10 megapascals. Underneath 0.0 to 20 Kelvin, excess fluid 1 to 14 from steam consumption, heat load from 1 to 60 times 10 to the power of negative 4 watt cubic meter, thermal pressure from 1 to 60 Kelvin, and system orientation 0 to 90 degrees. The studies revealed two areas of the process of liquid vaporization and the influence of regime and design characteristics of the internal and thermohydraulic characteristics. The optimal coolant flow rate and the most efficient type of mesh porous structures are established. Visual observations allow to describe the physical picture of the processing and summarize the experimental data on the internal characteristics and heat fluxes with an accuracy of plus minus 20%, depending on the thermophysical properties of the liquid wall, temperature, pressure, excess liquid, type of porous structure, and heat exchange surface. Depending on the ratio of maximum value of the wall temperature and the temperature of the working fluid on the saturation line, the priority may be a particular capillary porous material. For normal operation of the cooling system with the use of capillary porous material in its consumption composition, the value of the dimensionless temperature must be in the range from 1 to 1.3. The operating range, the definition of a particular capillary porous material depends on no less than 42 specific heat flows on the heat releasing surface in relation to their maximum value. In the operating range, delta Q equals 8.5 minus 10.2 megawatt cubic meters, and operating interval theta equals 1.25 minus 1 times 30. The following capillary porous material are possible, combined with a ratio of width of cells of a parietal layer and the subsequent 0.7 times 1 10 to the power of negative 3, single layer with cell width 1 times 10 to the power of negative 3, two layer with a layer thickness and width of wire with width of a cell 0.02 10 to the times of negative 3 meters. Determination of the type and characteristics of capillary porous material must be made in the general case by at least two criteria, dimensionless temperature and ST. It is also necessary to take into account a prior information about the project. Thank you for your time.